Good evening, and thank you for joining me for another Boring Books for Bedtime. I hope tonight's selection provides all the boredom your busy brain needs to quiet down and let you get some sleep. Before we begin, I'd like to give a special shout out of thanks to some new members of our Patreon family. Heller, Leela, Fence, Omega, Jessica, Emily, Peggy, and Brilliant Honey 8672. Thank you all so much for supporting this podcast. By becoming members of Patreon, you help us remain 100% listener supported and ad-free for everyone, and it's very much appreciated. If you're interested in supporting Boring Books for Bedtime and finding out more about the perks available to subscribers, including exclusive episodes, full books, and topical collections found nowhere else, you'll find a link to Patreon in the show description. You'll also find a link to buymeacoffee.com, where you can support us with a one-time tip. No subscription required. I hope you'll take a moment to check them out. Now, let's read and relax. Find a comfortable spot. Adjust your volume. Take a nice deep breath in. Let it out slowly. And off we go. Tonight, let's relax with more from a work written by a woman so remarkable that the word scientist was invented to describe her. We're reading On Molecular and Microscopic Science by Mary Somerville, author of The Mechanism of the Heavens, Physical Geography, Connection of the Physical Sciences, etc., in 2 volumes with illustrations. First published in 1869 by John Murray, Albemarle Street, London. Let's pick up right where we left off in the middle of Section 2 on force and the relations between force and matter. Let's begin. There cannot be a doubt that the atoms of a conducting wire are in motion, and that they successively take definite and momentary positions during the passage of an electric current, after which they return successively to their normal state. When electricity is invariably sent from the same pole of an inductive apparatus through the wire of a telegraph, in a very short time, the wire is torn or divided into small sections, which destroy its continuity. But when the electricity is sent from each pole alternately, the conducting wire is not injured, as each atom of the wire has its own electricity. This seems to indicate that during the successive transits of the same kind of electricity, the pole of each individual atom is attracted more and more in the same direction, till at last they no longer return to their normal state. The cohesive force is overcome, and a rupture takes place, the more readily if there be any imperfection in the wire. Since the electricity from the other pole of the machine would have the same effect, but in the contrary direction, an alternate motion in the atoms must maintain the continuity of the wire. A closed current of electricity or magnetism is accompanied by a simultaneous current of the opposite force in the tangential direction equal in quality and intensity. Thus the electric and magnetic currents, which are merely transmissions of energy, differ by moving at right angles to one another, Their effects are alike, yet they are not identical. The amount of the chemical action of light has been determined by Professor Roscoe to be directly proportional to the intensity of the light, and when the light is constant, the amount of action is exactly proportional to the time of exposure. It appears that equal volumes of chlorine and hydrogen explode in sunshine, but combine slowly in shade. And as the combined gases are absorbed by water as soon as combined, the gradual diminution of the volume of the mixed gases during the time of absorption is a measure of the amount of action exerted by the light. Professor William Thomson has computed, by the aid of Pouillet's data of solar radiations and Mr. Joule's mechanical equivalent of heat, that the mechanical value of the whole energy, active and potential, of the disturbances kept up on the ethereal medium by the vibrations of the solar light in a cubic mile of our atmosphere is equal to 12,050 times the unit of mechanical force. That is to say, 12,050 times the force that would raise a pound weight of matter to the height of 1 foot. The sensible height of the atmosphere is about 40 miles, whence some idea may be formed of the vast amount of force exerted by the sun's light within the limits of the terrestrial atmosphere. The green mantle which clothes the earth proves under a beautiful form the influence of light on the organic world. It has been proved that at any given fixed temperature, the amount of light and heat absorbed and that which is emitted remains constant for all bodies. The greater the amount absorbed, the greater the amount radiated. The molecules or atoms of the bodies, in consequence of the law of resonance, emit those ethereal undulatory motions which have been previously impressed upon them, as a musical instrument resounds in answer to the note impressed upon it. The whole is referable to molecular or atomic motion. For in absorption, the vibrations of the ether are communicated to the atoms, and in radiation, the vibrations are returned again to the ether. This principle is known as the law of exchange. Matter has a decomposing and an elective power with regard to both radiant light and heat. Most colored bodies, such as flowers, green leaves, dyed cloth, etc., though seen by reflection, owe their color to absorption. The light by which they are seen is reflected, but it is not in reflection that the selection of the rays is made, which causes the objects to appear colored. When light falls upon red cloth, a small portion is reflected at the outer surfaces of the fibers, and this portion, if it could be observed alone, would be found to be colorless. The greater portion of the light penetrates into the fibers, when it immediately begins to suffer absorption on the part of the coloring matter. On arriving at the second surface of the fiber, a portion is reflected and a portion passes on, to be afterwards reflected from or absorbed by fibers lying more deeply. At each reflection, the various kinds of light are reflected in as nearly as possible the same proportion. But in passing across the fibers while going and returning, they suffer very unequal absorption on the part of the coloring matter, so that in the aggregation of the light perceived, the different components of white light are present in proportions widely different from those they bear to each other in white light itself and the result is a vivid coloring. In certain substances, however, as gold and copper, the different components of white light are reflected with different degrees of intensity, and the light becomes colored by these reflections. Gold is yellow by reflection. Red cloth is red by absorption. In the same sense, physically speaking, in which the red cloth is red, gold is not yellow, but blue or green. Such is in fact the color of gold by transmission through gold leaf, and therefore gold is greenish-blue by absorption. In this case, we see that while the substance copiously reflects and intensely absorbs rays of all kinds, it more copiously reflects the less refrangible rays, with respect to which it is more intensely opaque. In general, absorption and radiation are independent of color. There is a vast diversity in the property which substances possess with regard to the transmission of radiant light and heat. Glass, for instance, transmits light abundantly, but is impervious to heat from non-luminous sources, while other substances, which are altogether opaque to light, transmit heat copiously, as the bisulfide of carbon, which of all liquids is the most diathermic, while water in all its forms is almost impervious to heat. Sir William Herschel discovered that invisible rays of high heating power exist beyond the red end of the solar spectrum, and Mr. Tyndall has shown that the reason of a substance being impervious to the light of the most brilliant flame, and at the same time pervious to those extra red rays, is that the intercepted rays of light are those whose periods of recurrence coincide with the periods of oscillation possible to the atoms of the substance in question. The elastic forces which separate these atoms are such as to compel them to vibrate in definite periods, and when their periods synchronize with those of the ethereal waves, the latter are absorbed. Thus transparency in liquids as well as in gases is synonymous with discord, while opacity is synonymous with accord between the periods of the waves of ether and those of the body on which they impinge. All ordinary transparent and colorless substances owe their transparency to the discord which exists between the oscillating periods of their molecules and those of the waves of the whole visible spectrum. The general discord of the vibrating periods of the molecules of compound bodies with the light-giving waves of the spectrum may be inferred from the prevalence of the property of transparency in compounds, while their greater harmony with the extra red periods is to be inferred from their opacity to the extra red rays. Water illustrates this transparency and opacity in the most striking manner. It is highly transparent to the luminous rays, which demonstrates the incapacity of its molecules to oscillate in periods which excite vision. It is as highly opaque to the extra red oscillations, which proves the synchronism of its periods with more of the longer waves. If then to the radiation from any source, water shows itself to be eminently or perfectly opaque, it is a proof that the molecules whence the radiation emanates must oscillate in extra red periods. It has been already mentioned that many substances which transmit radiant heat freely radiate badly, and vice versa. Rock salt is extremely permeable to radiant heat, but radiates feebly. The reason, according to Mr. Tyndall, is that the motion of the molecules of the salt, instead of being expended on the ether between them, and then communicated to the ether external to the mass, is transmitted freely from molecule to molecule. Alum is exactly the reverse. Mr. Balfour Stewart proved that alum is an excellent radiator, and Mr. Tyndall proved it to be a very bad conductor, imparting freely and with ease the motion of its molecules to the external ether, and for that very reason it finds difficulty in transferring the motion from molecule to molecule. The molecules are so constituted that when one of them approaches its neighbor, a swell is produced in the intervening ether. This motion is immediately communicated to the ether outside, and is thus lost for the purposes of conduction. Maloney had investigated the laws of the radiation and absorption of radiant heat in solid and liquid matter, but its radiation and absorption by gases and vapors was unknown previous to the experiments of Mr. Tyndall. The apparatus employed was a horizontal brass tube 4 feet long, between 2 and 3 inches in diameter, polished inside and closed airtight at each end by a plate of rock salt, which transmits more heat than any other substance. The air could be pumped out of the tube by one pipe, and the gas or vapor for the experiment introduced by another. Close to one end of the brass tube, there was a thermoelectric pile connected with its goniometer. On each side of this arrangement, there was a vessel of water kept at the boiling point. These 2 vessels were so placed that when the rays of heat from one of them passed through the exhausted tube and fell upon one face of the thermoelectric pile, their effect was so neutralized or balanced by the rays of heat falling on the opposite face of the pile from the other. Thus the needle of the goniometer was steadily maintained at 0, and its deflection instantly showed the absorbent effect produced by any gas or vapor that was admitted into the exhausted tube. Since aqueous vapor has a very exalted absorbent power, a gas or vapor was rendered perfectly dry before its absorbent capacity was determined. For that purpose, the pipe that introduced it into the brass experimental tube was so constructed that the gas had first to pass over fragments of pumice stone, wet with strong sulfuric acid, which absorbed its moisture and dried it. Common atmospheric air, however, was not only dried in this manner, but it was deprived of its carbonic acid by passing over caustic potash, and many other precautions were taken to prevent the possibility of error. Under the ordinary pressure of the atmosphere, when the experimental tube was exhausted, the needle of the goniometer stood at 0, but as soon as pure, dry atmospheric air was introduced into the tube, its absorption caused the needle to move from 0 to 1 degree. The tube was again exhausted. The needle stood at 0, but was deflected from 0 to 1 degree as soon as the tube was filled with oxygen. A similar experiment was made with nitrogen and hydrogen with the same result. Thus, dry air and the elementary gases, oxygen, nitrogen, and hydrogen, have the same absorptive power, and consequently, they all deflected the needle of the goniometer 1 degree. The whole amount of radiant heat that passed through the exhausted tube produced a deflection of 71 degrees 5 minutes. hence taking as unit of heat the amount that would deflect the needle 1 degree, the number of units expressed by 71 degrees 5 minutes is 308. Consequently, the absorption of each of these 4 gases amounts to 1/308th, or 0.3%. The most delicate tests could not show any difference between the 3 first, but Professor Tyndall had reason to believe that hydrogen has the lowest absorptive power of all gases and vapors, though he was unable to express the amount. The absorptive power of all 4 is very much less than that of every other gas or vapor, and invariably deflects the needle to 1 degree, which thus becomes the unit of comparison. Olefiant gas, the most luminous of the constituents of coal gas, possesses the highest absorptive power of the permanent gases. When sent into the exhausted tube, it deflected the needle of the goniometer from 0 degrees to 70 degrees 3 minutes, which is equivalent to 290 units. The whole heat that passed through the exhausted tube before the gas was admitted produced a deflection of 75 degrees, or 360 units. Consequently, more than 7/10, or 81% of the whole heat was cut off by the olefiant gas. Such opacity to heat in so transparent a gas is quite marvelous. A current of it was sent into the open air between the thermoelectric pile and one of the sources of heat, and although it was perfectly invisible, it instantly deflected the needle of the goniometer from 0 degrees to 41 degrees. In order to ascertain the relation between the density of the gas and the quantity of heat extinguished or absorbed, an ordinary mercurial gauge was attached to the air pump. The experimental tube was exhausted, and the needle of the goniometer stood at 0. Then, from a graduated glass vessel, measures of olefiant gas, each amounting to 1/50th of a cubic inch, were successively sent through the drying pipe into the exhausted tube. The amount of the heat absorbed and the depression of the mercurial column corresponding to each measure of gas as it was introduced was registered from 1 to 15 measures. This experiment showed that for very small quantities of gas, the absorption is exactly proportional to the density or tension. One measure of the gas only produced a depression of the mercurial column amounting to the 1/367th part of an inch, or about the 1/15th of a millimeter. In many of the vapors of volatile liquids, the preceding law only prevails to a certain amount of pressure differing in each case, beyond which increase of tension produces diminished effects. In sulfuric ether, the change begins at the 11th term. In bisulfide of carbon, the law changes after the 6th measure, etc. In order to adapt the apparatus for experiments on colored gases, a glass experimental tube 2 feet 9 inches long and 2 feet 4 inches in diameter was substituted for the brass tube, and instead of boiling water, sources of radiant heat having a constant temperature of 270 degrees centigrade were adopted. The following table shows the absorption of a number of gases at a common pressure or tension of 1 atmosphere. Dry air, 1. Oxygen, 1. Nitrogen, 1. Hydrogen, 1. Chlorine, 39. hydrochloric acid, 62. Carbonic oxide, 90. Carbonic acid, 90. Nitrous oxide, 35.5. Sulfuretted hydrogen, 390. Marsh gas, 403. Sulfurous acid, 710. Olefiant gas, 970. Ammonia, 1195. The absorptive power of ammonia is so great that although as transparent in the glass tube as if it had been a vacuum, a length of 3 feet of it would be perfectly impervious or black to the heat here employed. Yet even this does not express the energy which it exhibits under 1 inch of pressure. When the relative absorptive actions of gases and vapors is compared, it must be under the same amount of pressure. Hence, for 1 inch of tension, the absorptive action of dry air equals 1. Oxygen, 1. Nitrogen, 1. Hydrogen, 1. Chlorine, 60. Bromine, 160. Hydrochloric acid, 1005. Carbonic oxide, 750. Nitric oxide, 1590. Nitrous oxide, 1860. Sulfide of hydrogen, 2100. Ammonia, 7260. Olefiant gas, 7950. Sulfurous acid, 8800. Thus, for a tension of 1 inch of mercury, the absorption of ammonia exceeds that of air more than 7,000 times. The action of olefiant gas is 7,950 times, and that of sulfurous acid 8,800 times greater than the absorption of air. The effect produced by 1/30th of 1 inch of tension of air and the elementary gases is equivalent to that produced by 1 inch in the others, so the unit representing the absorption of these 4 gases is only the 1/30th part of the unit in the preceding table. It appears from the preceding tables of comparative absorption that chlorine, a highly colored gas with a specific gravity of 2.45, has an absorptive power expressed by 39 degrees under the pressure of 1 atmosphere, while at the same tension, hydrochloric acid, a chemical compound of chlorine and hydrogen, which is perfectly transparent, with a specific gravity of only 1.26, has an absorptive action amounting to 62, whence it appears that the chemical change which renders chlorine more transparent to light makes it more opaque to obscure heat. Again, bromine, which is far less permeable to light than chlorine, and has a specific gravity of 5.54, has an absorptive power of 160 under a tension of 1 inch, while hydrobromic acid, which is perfectly transparent to light, has an absorptive action for obscure heat amounting to 1005. This is a striking instance of transparency to light and opacity to heat being produced by the very same chemical art. The enormous difference between the absorptive power of compound and simple gases and vapors is ascribed to their atomic structure. In fact, the radiant and absorptive powers augment as the number of atoms in the compound molecule augments. The three elementary gases are formed of simple atoms. The compound gases and vapors consist of different kinds of atoms, chemically united into groups. Both are free to receive the vibratory motions of the ether which constitute heat. But single atoms must produce a less effect than when a number of them are united into a molecule. The atoms are unloaded by their chemical union, which offers a greater surface of resistance to the vibrations of heat, and renders the motion of the molecule more sluggish and more fit to accept the slowly recurrent waves of the obscure heat that strike upon it. Thus, when atoms of hydrogen and nitrogen are mixed in the proportion of 3:1, the absorption of the mixture is represented by unity, but when they are chemically united in ammonia, the absorption is 1,190 times as great. Atoms of hydrogen and oxygen, mixed in the proportion of 2:1, absorb very feebly. When chemically united into a molecule of aqueous vapor, the absorptive power is enormous. The absorptive power of nitrous oxide, a chemical compound of oxygen and nitrogen, exceeds that of dry air 250 times, a convincing proof that the atmosphere is a mixture and not a compound gas. Olefiant gas at 5 inches of tension absorbs 1,000 times that of its constituent hydrogen. In fact, all the compound gases and vapors far surpass the simple elementary gases and dry atmospheric air in their capacity for absorption. Chlorine and bromine, which have so many singular properties in common, have this peculiarity also, that though simple substances respectively formed of homogeneous atoms, their absorptive powers are similar to those of compound substances, for the absorptive power of chlorine is 60 times that of the elementary gases, and that of bromine 160 times. This high absorptive power is ascribed by Professor Tyndall to their atoms being united into groups, which act powerfully as oscillating systems, instead of the feeble action of single atoms. Ozone is an analogous instance of the presumed union of homologous atoms into oscillating groups. By comparing the absorptive effect of ozonized oxygen obtained by the electric decomposition of water with that of the same oxygen deprived of its ozone by passing it over a very strong solution of iodide of potassium, Professor Tyndall found that ozonized oxygen possesses an absorption force 136 times greater than that of pure oxygen. The quantity of ozone producing this astonishing effect was too small even to admit of estimation, far less of measurement. This result induced Professor Tyndall to believe that ozone is produced by the packing of the atoms of elementary oxygen into oscillatory groups, and that heating dissolves the bond of union and allows the atoms to swing singly, thus disqualifying them from either intercepting or generating the motion, which as systems they were competent to intercept and generate. The indefinitely small and indivisible constituents of perfumes of plants and flowers are proved to be compound bodies by their absorptive and radiating properties. The dried leaves of a flower or aromatic plant, such as thyme, were stuffed into a glass tube 18 inches long and 1/4 of an inch in diameter. It was then inserted between the drying pipe of the machine and the experimental glass tube, which was exhausted, and the needle of the goniometer stood at 0. Then, when the air admitted into the drying pipe passed over the time and carried its aroma into the experimental tube, the needle was deflected, and from thence the absorption of the time was computed to be 33 times greater than that of the air which carried it. By the same process it was found that the absorption of peppermint was 34 times, spearmint 38 times, lavender 32 times, and wormwood 41 times greater than that of the dry air, which was unity as usual. When small equal squares of bibulous paper rolled into cylinders and moistened with an aromatic oil were substituted for the dried herbs, the absorption corresponding to the deflection of the needle was for dry air equal to 1, patchouli 30, sandalwood 32, geranium 33, oil of cloves 33.5, attar of roses 36.5, bergamot 44, lavender 60, lemon 67, orange 67, thyme 68, rosemary 74, oil of laurel 80, chamomile flowers 87, spikenard 355, anise seed 372. The absorption of thyme and lavender shows how much aroma is lost when plants are dried. So great is the absorption of heat that the perfume of a flower bed may be more efficacious than the entire oxygen and nitrogen of the atmosphere above it. The enormous absorption and consequently radiating power of the perfumes of plants and flowers is a proof that their constituent parts are molecules and not simple atoms, incredible as it may seem. The absolute weight of the substances producing these wonderful effects is unknown, but there must be great differences. Some perfumes are carried to vast distances, others are less volatile, and that of mignonette was remarked by Dr. Wollaston to be absolutely so heavy that it was quite as powerful below a balcony containing a box of that plant as in the balcony itself. The perfumes during the experiments adhered to all parts of the apparatus so pertinaciously that after a continued stream of dry air had been pumped through the tube till the exhaustion seemed to be complete, and the needle stood at 0 after a few minutes' repose, the residue of the perfume came out so powerfully from the crannies of the apparatus as almost to restore the original deflection. The quantities of those residues must be left to the imagination to conceive. If they were multiplied by billions, they probably would not obtain the density of the air. The absorptive power of the odor of musk was 72 or 74 times that of the air that conveyed it into the experimental tube. The quantity that produced it was quite inappreciable, yet the perfume was so persistent that the pieces of the apparatus through which it had passed had to be boiled in a solution of soda before they were fit for other experiments. The absorption of many gases and vapors having been determined, their radiation was measured by a very simple arrangement. The thermoelectric pile was raised on a stand with a screen of polished tin in front of it. A heated copper ball in a perforated ring on a low stand was placed behind the screen. All direct radiation from the ball was thus cut off, but the heated air rising in a column above the screen radiated its heat on the pile and deflected the needle of the goniometer 60 degrees when the ball was red hot. But the radiation of the hot air was neutralized by another source of radiant heat on the opposite side of the pile, which kept the needle steadily at 0. Then a purified gas or vapor conveyed by a pipe into the perforated ring which held the ball rose mixed with the heated air above the screen, but the radiation of the gas or vapor alone was shown by the deflection of the needle because that of the air was compensated. With this apparatus, Professor Tyndall proved that the amount of the absorption of each gas and vapor is exactly equal to the amount of its radiation. He has shown that this result is a necessary consequence of the dynamical nature of heat, for as no atom or molecule is capable of existing in vibrating ether without accepting a portion of the motion, the very same quality, whatever it may be, that enables it to do so, must enable it to impart its motion to still ether when plunged into it. Hence, from the existence of absorption, we may, on theoretic grounds, infallibly infer a capacity for radiation. From the existence of radiation, we may with equal certainty infer a capacity for absorption, and each of them must be regarded as the measure of the other. This reasoning, founded simply on the mechanical relations of the ether and the atoms immersed in it, is completely verified by experiment. Hitherto, the absorption and radiation of heat by the same thickness of different gases and vapors have been compared with each other. But in a recent series of experiments, Mr. Tyndall has compared the action of different thicknesses of the same gas or vapor on radiant heat. The experiments extend from a thickness of 0.01 of an inch to that of 49.4 inches. The instrument employed for ascertaining the action of the smaller thicknesses was a horizontal hollow cylinder closed at one end by a plate of rock salt. A second cylinder was fitted into this, with its end also closed by a plate of rock salt. This cylinder moved within the other like a piston, so that the two plates of rock salt could be brought into flat contact with one another, or could be separated to any required distance. And the distance between the plates was measured by a vernier. At one end of the cylinder, there was a source of constant heat, and the differential goniometer already described at the other. With this apparatus, Mr. Tyndall found that olefiant gas maintains its great superiority over the other gases in absorptive power at all thicknesses. A layer of that gas not more than 0.01 of an inch thick intercepted about 1% of the total radiation. This great absorption corresponded to a deflection of 11 degrees on the needle of the goniometer, and such was the delicacy of the apparatus that it would be possible to measure the action of a layer of this gas of less thickness than a sheet of writing paper. A layer of olefiant gas 2 inches thick intercepts nearly 30% of the entire radiation. A shell of olefiant gas 2 inches thick surrounding our globe would offer no appreciable hindrance to the solar rays in coming to the earth, but it would intercept and in great part return 30% of the terrestrial radiation. Under such a canopy, the surface of the earth would probably be raised to a stifling temperature. The apparatus for measuring the action of the greater thicknesses of gas was a hollow brass cylinder, 49.4 inches long, closed at both ends by plates of rock salt, and divided internally into two compartments or chambers by a third plate of rock salt, movable in the interior, the source of heat being at one end and the differential goniometer at the other. Carbonic oxide and carbonic acid are pervious to a vast majority of the rays of radiant heat. When the cylinder was filled with carbonic oxide gas and so divided by moving the internal plate of rock salt, that a stratum of the gas 8 inches long was next to the source of heat, and that 41.4 inches long farthest from it. The 8 inches of gas intercepted 6% of the whole radiation. But when the plate of rock salt was moved till the column 41.4 inches long was next to the source of heat, and that of 8 inches farthest from that source, or behind the long one, the absorption of the 8 inches was sensibly 0. In like manner, 8 inches of carbonic acid gas, when in front of a column of 41.4 inches of the same gas, absorbed 6 1/4% of the whole radiation, while placed behind that column, the effect was nearly 0. The reason is that when the 8-inch stratum is in the front, it stops the main portion of the rays which give it its thermal colors. While placed behind, these same rays have been almost wholly withdrawn, and to the remaining 94% of the radiation, the gases are sensibly permeable. It is inferred from an extension of this reasoning that the sum of the absorptions of the two chambers taken separately must always be greater than the absorption effected by a single column of the gas of a length equal to the sum of the two chambers. This conclusion is illustrated in a striking manner by the experiments. It is also found that when the mean of the sums of the absorptions is divided by the absorption of the sum, the quotient is sensibly the same for all gases. It may farther be inferred that the sum of the absorptions must diminish and approximate to the absorption of the sum as the two chambers become more unequal in length, and that the sum of the absorptions of the two chambers is a maximum when the medial plate of rock salt divides the long tube into two equal parts. When air enters an exhausted tube, it is heated dynamically by the collision of its particles on the sides of the tube as it rushes in to fill the vacuum. And when the tube is exhausted again by the air pump, chilling is produced by the application of a portion of the heat of the air to generate vis viva. This dynamic principle occurred in some of the experiments and was dexterously adopted and applied to the solution of a striking and unprecedented problem: to determine the radiation and absorption of gases and vapors without any source of heat external to the gaseous body itself. And before we leap into the long proof of that problem, I think we'll end this evening's reading from On Molecular and Microscopic Science by Mary Somerville. I confess, I'm quite good with science, but I mostly have no idea what she's talking about in this chapter, except for the proof that scents of flowers are made of molecules, which is in fact true. So that's kind of interesting. I hope you enjoyed that, or at the very least, were bored to sleep by it. If you'd like to read this work for yourself, as always, You'll find a link to a free ebook from Project Gutenberg in the show description. If you'd like to connect, suggest a boring book you'd like to hear read, or request more from one we've already started, you can drop me an email via our website, www.boringbookspod.com. It's always a pleasure to hear from you. Thank you so much for joining me for this evening's reading. Until our next boring book, good night.